Okay, I think everyone's here from yesterday, so unless there's more questions before we start, we can dive in. Fine to have more questions. There's nothing wrong with it. It wasn't a problem. Okay, so I'm just gonna have a couple of things before we pick up basically exactly where we left off yesterday. Just because of a couple of questions of things that we had. This is just a table taken from Benedict's Winter School talk, showing just kind of a basic nucleus, then the CQ of kind of the PET or model compound that's used frequently. So like deuterium for, H2O with, 230 megahertz CQ. So here you can see N14, which is the other spin one. It has, order of magnitude larger quadrupolar coupling, which means an order of magnitude broader spectrum. So now you can see the issue with N14 spectroscopy, that we have this problem of we only have, the two transitions there, single bond transitions there, and they're really broad, and you can't narrow that out, like we do with the central transition in spin half by just selectively hitting only part of the breadth. So now you have to excite megahertz broad line widths. I'm not going to talk about it, but there's ways that people try to go around this. There's overtone spectroscopy, which I don't know enough about and didn't spend all day this morning trying to get educated enough to be able to say anything about it. So we won't talk about it, but that is one way that people try to study N14. You'll see it here and there. Sort of if you go to ENC and you go to the Exotica section, there might be somebody who's doing N14 overtones of spectroscopy every now and again. For oxygen 17, here we have, sorry, I'm trying to write on my screen now. We have the, about 10 megahertz on here on the side.
First, it was supposed to be a spin 1/2, according to my misunderstanding of the nuclear model, and then they slam us with this 10 megahertz.
Yeah, and so here's another one we talked about. Here's potassium 39. So potassium has two spin active nuclei. One is half integer quadrupole, and the other is integer spin quadrupolar. So neither is favorable. I think they're about 77 and 27 or 67 and 37% abundant. So I can't remember which. I believe the 3/2 spin, which is 39, is the lower abundance nuclei. I think 40 is the high abundance one, if I'm not mistaken.
But they're both low gamma, right?
They're both fairly close. Actually, I'm fairly certain that it's one of the ones that people have tried along with chlorine, where you can actually detect both of them in the same spectrum. So it's really broad, but like chlorine has two spin half integer ones, 35 and 37. They both have massive quadrupolar couplings, unless you look at something like salt, that doesn't have a massive because of its tetrahedral environment. One thing I will note, it's not on here, which is, but if you do any solid state NMR, you will encounter a quadrupolar nucleus, almost certain. Because one of the first things that solid state NMR spectroscopists do is they check the magic angle of their probe. They do this by taking a spectrum on potassium bromide. On the bromide spectrum, it's a quadrupolar nucleus. It's one of the reasons why it's incredibly sensitive. Another nucleus you can do this with is the chlorine and sodium chloride. Chlorine 35 is pretty close to nitrogen, so you can tune your probe down, your nitrogen probe generally to it. In my PhD, we had a probe that was HON, pretty rare probe that exists in the world. And to check the magic angle of that, I used sodium chloride and looked at the chlorine. And the rotary echoes go out to around 30 milliseconds on that when it's really good.
Oh,
Yeah, they go out really far.
so you were looking at, you said you were using sodium
Sodium chloride.
chloride,
So just, I mean, just salt, just table salt,
but you're looking at the sodium or the chloride?
the chlorine.
With that 60, I know it's octahedral, but
Yeah,
still.
Yeah. So anyway, but that's the one that you'll invariably do some spectroscopy on. It's so near symmetric that pretty much all of these effects that we're talking about are you're not in the low limit anymore. You're not, your B1 field is not much larger, smaller than your quadruple coupling, because your quadruple coupling is tiny. Because this is just essentially what you're seeing is just imperfections in the actual crystals.
Otherwise, if it was perfectly octahedral,
You would,
there's nothing to tune
yeah,
up
there'd
on.
be nothing to see, so you wouldn't be able to use it. This is just looking at specifically oxygens. So these are different oxygen moieties mostly in biological systems, and you can see sort of carbonyl and carboxylates have the smallest quadrupolar couplings. And here's the span of their chemical shifts. This is taken from that review that I took the chemical shift ranges from that I was showing earlier. So, some of them, like this, group here, have up to 3,000 ppm CSA spans. So your CSA is a major problem as you eliminate your quadrupolar coupling, which can be up to 15 megahertz by going to, let's say 40 Tesla, going to 1700 megahertz, your CSA is going to be huge. And to spin it out, you'll need to be spinning at 100 kilohertz, just to detect the oxygen without, massive overlap of the spinning side bands. So, and then there's some here where you have very small CQs, but very large CSAs. These are these heme motif ones.
You have small C.
So. Well, the other problem is when your CSA is around 3,500, it's hard to measure the CQ sometimes because you can't get a good spectrum to actually measure what the breadth, and get good line shape analysis. Because obviously the CQs are all coming from line shape analysis, NMR, that are coming from NMR. And the other option is that you can do NQR, which is Ann mentioned. You can go at zero field and actually measure the quadrupolar coupling directly. So the other thing that I was just throwing up, this is similar to something that Ann showed. This just shows the frequency of the different NMR active nuclei with, blue, the cool colors being higher frequency, and then the red ones being your low gamma nuclei. So, like oxygen is red, 5 to 8 megahertz per Tesla, carbon, then this orange, 8 to 12 megahertz per Tesla. Nitrogen isn't even NMR active in, most, but it's really low. It's really low. Most of it's N14, which isn't shown here what it is, but it's showing the one that most people use. So this potassium one here is in the white, so 0 to 5 megahertz per Tesla. So you can see the ones that, that jump out, things like lithium-7 and proton, fluorine, phosphorus, yeah, tin.
Tin is nice.
Thallium.
Some of those are like in the no man's land where we can't tune most of our probes.
Yes. Yeah, the big problem is that once you get sort of in between fluorine and phosphorus, most probes aren't tunable there for reasons that there's not much in that section, and so it's not worth designing a probe that tunes to that. And in most cases, people who have done those kind of studies have done them on single channel probes that don't even have a proton channel, just X. Because most of the time, if you're looking at something like tin or thallium, you probably don't have a lot of protons around. You don't have to worry about decoupling the protons like we always think about. So you don't need the proton channel. It's not adding anything, so to speak, to the game. Okay, so that was just kind of a couple of things just from what we talked about yesterday that had come up. So I should have included the slide before this on here. Just to kind of remind you, I had started with, actually, I'll go back just so we had ended yesterday with the results that I had found we looked at the results in bound waters of oxygen 17. These are direct detect experiments. Nisha was asking, directly detecting the oxygen 17, I don't know if I said proton, the oxygen 17 of the water. So one advantage to using direct polarization in these cases is your T1 is usually on the order, at least in these waters, they have motions, they're hopping back and forth. There's other emotional aspects that are happening. We'll talk a little bit about that later. And so their T1s with it being quadruple nucleus is on the order of hundreds of milliseconds. So you can rep these incredibly quickly. It actually turns out that at room temperature, the hopping motion decouples proton couplings, and so you don't even have to proton decouple the oxygen 17s in the water at room temperature. They're self-decoupled by the motions themselves. So that was kind of odd, and giving it away. I had posited the question, why is quadrupole coupling tensors being almost identical for all these different water molecules in different single crystalline amino acids? Why is that interesting? Why is that something is that something you'd expect to see? Sort of, they all have exactly the same electric field gradient. They have different chemical shifts. We showed a chemical shift dispersion. So their chemical shift tensors are not all the same. They don't have a wide range of CSAs. That might not be, that might be something, but for the electric field gradient, I'll just say this, it's not what you would expect.
Water is considered one of the most polarizable. This is what makes MD hard, right? It's like so hard to have a one size fits all model for water and MD with fake charges and everything.
Well, I mean, in some ways, this is, we're looking at bound water, so it's a little bit different. It's not.
One would hope for more variability, not less.
Right. So yeah, so this comes into play. So how do we think about this? I guess I didn't really talk about it too much, but it's a very right field doing DFT calculations on quadrupolar nuclei and studying it that way. It's one of the additions other than multiple fields to help you fit your spectra, run DFT. There's a lot of programs out there that are very, very good at predicting the electric field gradients for molecules. So while there still is plenty of issues with the chemical shifts in those molecules, the EFGs, if you're using the right force fields and the right kind of program, the right waves, you should get pretty close at that. And particularly if you're trying to do something like looking at non-spinning or static NMR spectra and looking at CSA quadrupolar interactions, you should run DFT to start off with, so that you have some idea what the incident angles between the two tensors are, rather than just scattershotting trying to find them, because it's very good at finding the incident angles between those two interactions. It might not be very good at finding the magnitude of the CSA or anything like that, but it's very good at finding the angles of those two interactions.
And I just want to reinforce that by saying one of the papers that I read, and I recommended, but not unless you read some of the more basic stuff first, but it's a consideration from somebody called Pascal Mann, who's talking about why echoes are so hard and things like that. And anyway, at some point, he says in passing that when people are fitting, don't try to get these angles out of just fitting your data. And he said, you know, some of us just set them to 0, 0, 0, knowing that that's nonsense. But I really like what Eric just said about it better, because I feel like that's definitely true for CSA, which is harder, because it's an excited state property. Like the angles, they're always right. So just get it from the simulation. Sounds good.
Yeah. So, okay, so we did DFT, we did GPA calculations of this, and as you can see, the calculated versus.
Sorry, what's GPA? Sorry for interrupting.
Sorry, gauge independent, I don't know what the P is, augmented waves. It's
Somebody's program?
yeah, it's actually the waves, the program is FastStep.
Never used.
So it's used widely in quadrupolar NMR. So but it's a very specific thing that it does EFGs very, very well. So it's implementable in multiple programs. So I have I can't see them, but I have a presenter note that actually tells me what it is. What GPA means, because I always forget the P. I don't know why I forget it, but I can't remember. But anyway, so we ran these calculations. They're quantum chemical calculations that are used to predict EFG tensors. And as you can see, they don't predict anything in comparison to the experimental. I mean, as I said, they're all almost the same in the experimental. So you have this big, vertical line here, but they're not in the calculations. Quantum chemical calculations say this should be incredibly sensitive to what's going on structurally, the structural differences, because obviously the bound water itself, the local structure of the bound water is not changing between them. You're not seeing a lot of variability in the, HOH angle or the HO bond distances. If you can find a neutron structure that actually has them, there's not that many of them. Most of them don't have accurate protons, so these bound waters aren't really well characterized there. But there's not the thought that this is not coming from this variation that we're seeing is not due to local changes in the water itself, but secondary structural differences between what we would expect would be hydrogen bonding networks in these different crystals.
So that's really
So, look
analogous
at
to
that.
the deuterium literature where, they like to fit hydrogen bond metrics to the quadrupole coupling.
So if you just look at the hydrogen bond distance, the nearest nitrogen oxygen, bond distance in these versus the calculated CQs, you can see that that's a pretty good
Nice line.
linear. It's not a fit, it's just but mainly because this is calculated, the X-ray or neutron structure, data. So it's not a perfect thing, because obviously we didn't measure these different CQs, so we can't say that this is really what we're seeing. But the thought is, from our perspective, is that these waters undergo multiple different motions that are causing averaging that's happening in the hydrogen bonding. And so in a moment in time, when you do a 77K or 4K neutron structure, you see a hydrogen bond that's there. But if you have on the room temperature NMR time scale, we have this exchange of these two protons due to rapid flipping. We see this bond network isn't strong enough to see it in the EFG tensors. They're getting averaged. Those EFG tensors are being averaged in that way.
And these are room temperature measurements, are they?
Everything's room temperature. So obviously this says that there's an opportunity, assuming that, that there's not something wrong with how the EFG or how the quantum chemical calculations calculate bound water oxygens versus, say, carboxylate oxygens or any other oxygen that, these calculations get very, very, very accurately approximated. So I think that, our conclusion was that this should be something that we can look at, but room temperature is not the right place. Or if the water is, too free to sort of hot and vibrate, it's not going to yield sort of what you would expect. So that was kind of what came out of that. I just put that just.
Are there low temperature measurements yet?
Not of those ones. But we'll get to.
Yeah.
So the next step is, well, maybe we can do something simpler because those things, there's a lot of other things happening in an amino acid. You have all kinds of other nuclei, there's other motions. Let's just get down to something much more understood. So we looked at barium chlorate monohydrate. This is a sample that's been done for years.
Well, we did do this compound over and over again.
Yeah, it's been floating around for a long time in the mind. No, I think that measurements done, I want to say in 70s out of Stanapella's group is some of the work that's been done on the compound itself. So here I'm just kind of showing on the water molecule different orientations of the tensors that were fit out using both quantum chemical calculations to help get the angles. This is actually the picture is actually coming straight out of the cast up calculation. So programs that you can take the tensors and then draw their principal axis components on, and then I added the dipole, obviously, just afterwards with theirs. So these are once again direct. So we take three different things. We took MAS spectrum. We get what we saw yesterday. We took a stationary spectrum, so we're not spinning. It's still in a magic MAS probe. And then we've added proton decoupling, and then we turn the proton decoupling off, and then we simulate all of those iteratively. So I could have done it simultaneously. I didn't. I just did them iteratively by hand. So I fit one, take those parameters into the other one, refine, then move to the next one, refine, and then go back, and then just keep doing that until they all minimized sort of the shape. You can see in this case, we only have one water. Everything's pretty good. The CQ and eta Q are pretty much right on line with what we've had with all of our found water so far. So everything's looking good here. Obviously, this is at room temperature. But this once again, while the shape is good, I didn't write it down here, but I believe the cast step GPOW had something on the order of approximately 8 megahertz with an eta. That's approximately, I want to say it was around 0.75.
That's the dotted line again?
No, the dotted lines are fits. So this is experiment, and then that's just a fit.
Right, but cast step, that's not how you fit it. You fit it with something else.
I fit these with either Simpson or DM fit. I can't remember which one I used for these particular ones, but
And the assumption is these are all central transitions.
yes.
So you get considerable narrowing with MAS, but
Yes.
it's still 20 ppm broad or something.
Yeah.
So
Yeah, so
there's
this
a
is
lot
the
of
central.
hope to resolve two waters in the same sample in this way.
Let's
Yeah,
we'll get there
later, yes, but not in this.
we're building here on this. So the next step is what happens if we cool it down? Well, it turns out that there's NQR data on this particular sample from 1976, operating at 77 Kelvin. They got a CQ, and NQR, we can only get the magnitude, so we don't have an asymmetry, but we have that they said it was 7.6 megahertz polar coupling. So it's still not quite what you'd expect from quantum chemical calculations, but those are obviously calculations that are done at 0K. They're done with no thermal assumptions. So then we took it and we went up the road to Villarica, where they had DNP probe that can cool and tune to oxygen 17. And so this data is at 600 megahertz. The previous data was I believe at 900 or 700 in-house, spinning at 14 kilohertz. So you can see the spinning sidebands coming in. We took data, again at 300 Kelvin. We fit it again and got the same, same result. This is actually, this fit was included in the other fits when I did all the fitting. Then we cooled it down. We cooled it down to 170. The reason why this spectrum doesn't look quite as good is because it's actually pretty hard to hold a temperature like 170 Kelvin on a lot of DMP probes. They're not designed to hold sort of in between temperatures. They go down to around 100K. They like being down there. They're fine at room temperature. Something in between is a little hard just because you have, 90 to 100K cooling gas going into the probe. You're heating that to get it to 170K. And so it's just hard to maintain that amount of heating on it the way they have it designed. It's also that at 170K, the density of nitrogen is pretty strongly changing. And so spinning is difficult in Bruker DMP probes. Spinning gas, drive fairing, and BT are all cooled. So you have issues maintaining a stable spinning frequency for long periods of time. So this was a experiment where we took for on the order of an hour or so, and the other ones were taken for a little bit longer to have better signal noise. But that's just why it's a little less signal noise. And lo and behold, the CQ is larger. Quadrupole coupling is larger, and the asymmetry has gone down. So it's not almost an 8=1 tensor. A little bit changed in shape. The easiest way to see that is if I drew these lines here. We have sort of the left edge of the spectrum near the isotropic chemical shift of this. If you recall previously that I showed that basically as you get bigger in this and the spectral, it just kind of moves this way in these spectra. So then I just drew a line that's sort of the right edge, turning edge, and you can see it moving out in time, and the spectrum's actually broader. Then we went down to 105K, and we get 7.5, and once again, now we're down to about 0.9, and that's what the spectrum is here. Now, there's a caveat on this, and the caveat is that this has proton decoupling in. There's no proton decoupling in the top two spectra. The bottom spectra is proton decoupling. I'll show you why. So at 105 Kelvin, the hopping rate is slow enough that those protons are reintroduced, and they're not moving, and you get.
That's cool.
Well, sorry. So you get a very different spectrum. We'll go over it in a minute.
Eric, just once again, and I know I asked this already. And by the way, the 105 Kelvin is a nice spec.
Yeah.
But everything, including asterisk, means spinning sidebands, right?
Yeah. This asterisk for spinning sidebands.
But we think everything here is central transition.
Yes, it's all central. Yeah, the satellite transitions are. They're there. In fact, this might be part of one. That little tiny hump there.
It's very familiar with this spectrum.
Might be
this thing right here.
Might be part of it. Might be the far edge on that side. So I mean, some of it is not 100%.
Basically.
Yeah. So the question is, what is causing this to happen? Why are we seeing this increase in the quadrupole coupling? So we think about the motions in the molecule. They're well understood. There's sort of two different motions we talk about. There's the hopping. So that is, an exchange across this axis of the two protons that happens, at a rate that I don't know off the top of my head, but it's quite fast. And then there are other motions that have been studied. There's librations that are happening. So you have sort of rocking, they're called rocking, waving, and twisting motions of this OH bond. So now the question is which of these motions do you think is causing this averaging of the quadrupolar coupling? I'll go back just for a second so that you can see where these are on the molecule. So I can draw it out. We have along this axis here, we have VXX. Along this axis here, we have VYY. And coming in and out of the page here is VZZ. Just to remind you, CQ is proportional to VZZ, and eta Q is equal to VXX minus VYY over V. So I haven't told you anything about where the librations are happening, but do you think the hopping motion has any effect on the quadrupole coupling?
The asymmetry of the,
What?
on the asymmetry.
I think that's an identity of, if I'm the oxygen, other than the decoupling issue, which was interesting, do I really care? Left, right, whatever, who's here, who's there, as long as there's somebody on each spot at all moments, do I care? Who's who?
Yeah, and one of the big keys there is that the quadrupolar coupling, which is what we're seeing mostly moving in this instance, is proportional only to one of the tensor elements, the VZZ. It's coming in and out of the page. If I swap those two protons, what happens to that? Nothing. If I swap the two protons, what happens to the other ones? Nothing, because it's not. If it was a continuous motion, you could imagine it now. You know, YY is moving through space like this. You know, XX wouldn't be, but you could imagine YY is changing. But we know that this is a discrete hop motion. That's deuterium NMR has shown that it's not a continuous fusion around there. It's a hot motion. So we don't think it's this. So that leaves us with librations. Now that's not something that we generally think about much in an MR, because they happen pretty fast. They're not something that they're fast on ours. They're, you know, what we would generally call quasi-static.
Already includes that, right? You're talking about librations and that kind of thing.
Yeah.
We call it static, but we're just
Yes.
kind of,
Yeah, so we would say it's quasi-static because on the NMR timescale, it's too fast. It just causes whatever effect it's causing is part of what we're seeing, but we can't see its effect in any way in general. It turns out that if you look at these motions, so we have twisting, waving, and rocking on this diagram. So rocking is about, you know, this axis that comes in and out of the sensor. Waving is, you know, along the, you know, axis that's parallel to the, you know, HOH plane, and then twisting is from the top of that oxygen moving those out. So we have, of those, we have two motions that affect the ZZ component, which is what we're measuring with quadrupolar coupling, the actual magnitude. The asymmetry is different. They're going to be affected in different ways. Because all three components go into the asymmetry. But right now we're just saying we've seen a really large change in the quadrupolar coupling that's easily measurable. This asymmetry change is more subtle. It's there, but it's not nearly as sort of jump out at you. Wow, the spectrum is getting bigger. And so if you look at these two motions, we have the sort of waving and the twisting motion. The rocking motion is not going to do anything to the oxygen because it's just rocking about the VZZ axis. So VZZ is just staying right there. But if you think about these other motions, we're moving this way in space. And this is just the same motion shown twice just to show. And you can imagine that what's happening is that VZZ component of that tensor is moving up and down here and side to side here. And so if that's happening fast on the time scale of our measurements, what we will see is an averaged tensor. So an effectively shorter version of this VZZ. Obviously, this is, it's a tiny, tiny change. I'm showing massive, massive changes, but we have an effective tensor that's shorter, and so a CQ that's smaller. So I mentioned that we turned on proton decoupling. So what happens if we don't proton decouple when we're really cold? Well, this is what happens. We get this spectrum right here. So the protons are back. And to simulate this spectrum on the bottom, I used Simpson, which is a full time domain spin simulation program to fit this spectrum. And I had to include all of these interactions in it, not just the OH dipole coupling, but the proton-proton dipole coupling needs to be included. That's what gives rise to this splitting here.
Oh, that's complicated.
Yeah. So it turns out, I mean, these are very, very strong. This is a, 21 kilohertz.
The OH or the
HH. The HH is
Yeah.
a 21 kilohertz
And the OH is
dipolar coupling.
something big too, right?
Yeah, it's fairly large. I don't have the numbers off the top of my head. But so this is what happens when you decouple them.
You lose those sidebands or something with it.
I mean, the sidebands also have the effects in them too. So that's
No.
why you get these really weird, and the sidebands, as you can see, they don't really fit very well to the experimental sidebands, but it turns out this is incredibly complicated. So we felt pretty good about how well I could fit this, but
Terrible. I mean, it's
so anyway, so this is just something to think about. If you're going to do bound waters at DNP temperatures, you're going to need to decouple. Otherwise, you're going to get this other spectrum. And if you thought this one was going to be bad to try to look at multiple waters, this one is going to be an absolute nightmare. It actually didn't get that much broader, but you have multiple horns. So you don't have any indication that this isn't two waters all of a sudden, but except for we can simulate it and we know there's only one in there.
yeah, right.
So we also looked at these are in this is simulations done from called Pi Gamma by, I didn't write his name down, which I should have. A postdoc from Tom that was in our group. This was after we published our paper, and we were talking about various different things. And he was just like, oh, let's see what it looks like if we actually include the exchange. It's not something that I had access to in Simpson. I didn't know Pi Gamma's formalism, so I wasn't familiar with it. He came from, the group of Niels Nielsen. He had a lot more experience in these sorts of programs. So, so you can see as the exchange goes from, essentially infinitely fast to, 1, you get the spectrum that we expected. Somewhere in the middle, you actually get a spectrum that looks kind of similar to, like around here, that looks fairly similar to the sort of discrepancies in the shape that you see as I go back, sorry. In here, where suddenly it's a little bit broader, these sort of two sides are more evened out. This was something I didn't think about when I was actually fitting these, but that's likely due to the motion being on a time scale that we actually can, the hopping motion being at a time scale that is actually affecting the spectrum as well because of those protons. And this is because this has no proton decoupling spectrum. So if we proton decouple, that would go away.
What was the type of motion did you assume with that? I guess it's
Twofold hop.
oh,
It's a twofold hop is what is the motion that's being simulated, not the librations.
okay.
This is the twofold hop. The pi gamma simulations are a twofold hop.
And I
Exchange of the two protons. Essentially, we're just exchanging the two protons every, 20,000 times every second. And the one I've circled.
and again, those two models in the slow exchange limit, are they because of ineffective decoupling, or are they because of how two different isotropic?
There's no decoupling in this. There's not two different isotropic. This is an effect because of the strong proton-proton dipole coupling. It's a splitting that happens because of that.
I would assume that hop doesn't completely average the dipole coupling. It might put you in a place where the dipole coupling is much narrower or is an intermediate exchange, in which case decoupling doesn't. It's hard to get any traction out of just applying the RF. But then if you go all the way to the fast limit, when you're really warm,
I think
there's probably some remaining dipole coupling that's much weaker. What do you think?
I can go over some of this. Basically, I think when it's hopping, the proton-proton is effectively decoupled from the oxygen. So the second order effects that are causing this splitting, those are gone.
That's a really good point, because that
Because
wouldn't
I've
be the
done
right
simulations
symmetry to
when I-
actually get rid of the proton-proton, and then the proton-oxygen could mostly
The
spin out.
the proton-oxygen is spinning and
Yeah.
is
Yes,
getting
that's a
rid of
really
that,
good
and its effect is much smaller. So I did simulations where I looked at taking out one of the
I forgot
effects and
about
seeing
that,
what
yeah.
happens. If you take out the proton-proton coupling, you don't get the splitting at all. You just get, stronger side bands, a little bit.
Right. It's
broader,
like it's
uglier.
mostly spinning out, right.
So most of it's spinning out on there. So it's really this hop coming down and bringing back in the proton-proton coupling. So it's not something we generally think about, including these sort of homonuclear couplings in an experiment of a different nucleus. So it's just a interesting thing. But when you have very, very strong interactions, proton-proton here is incredibly strong. You can't necessarily, with quadrupolar nuclei, you can't necessarily discount the effect of that effect in between the dipole coupling of homonuclear dipole coupling of one nucleus and the quadrupolar coupling of an attached nucleus or nearby nucleus. So these are things that you don't think about generally in spin half nuclei because the couplings are not strong enough that you see those effects being large in there. There was a time when I was looking at trying to measure some things in a similar sort of system between carbon and proton, but I never got the sample actually running and such, but would have been interesting to look at.
I bet you'd have something.
Yeah,
Really, yeah.
you can
that's
see it.
cool.
I did simulations. You can devise systems that
Yes.
spin half where you see this effect as well.
That's a really good point.
Okay, so then what's the next step? Well, can we resolve multiple waters in the same sample? So once again, we move to something that's not really biological, but what we're doing is we're trying to say, what if we want to look at multiple waters? What's a fairly simple system? One big issue with these is everything I've shown you here, we're operating with labeled samples. These are not natural abundance oxygen 17 spectra. These are labeled for most of the amino acids, around 30% labeling. This is achieved using, in those instances, using acid catalyzed exchange. So you put oxygen 17 labeled water and amino acid, you put it with concentrated acid and you let it exchange, and then you isolate out the amino acids and they've exchanged with the O17s. Obviously, this is kind of a harsh environment to do this in. It works for amino acids. Once you get to anything bigger, you're just going to destroy your molecule with the sulfuric acid that you use. So, but in this case with, lithium magnesium nitrate, hydrate, we can do this as well. So we have, this is the molecule we're looking at here. It has 24 bound waters in its unit cell. Shown up here, if you look at the neutron diffraction structure, you can pull them out into 4 different water molecules based on their bonding environment. So there's 4 different ones. So if you look at the neutron diffraction and then you do, DFT calculations on them, they group as 4 different ones with slightly different chemical shifts, slightly different CQs, all of that. So what then happens if we take a spectrum of it? So I didn't write it on here. I should have. Spectrum on the left is at 500 megahertz. The spectrum on the right is at 900 megahertz. Now, we're seeing a central transition like we'd expect. We're spinning, in a 3.2 millimeter rotor, we're around 24 kilohertz. In the first spectrum, you see something that looks fairly similar to everything we've seen before. If you look really, really closely and you spend a bunch of time looking at it, you can see that there is a shoulder right here on the spectrum, and a little bit of a difference on this side. It's kind of hard to tell. Underneath is a simulation using 4 different individual O17s to fit it. When you go to 900 megahertz, you can see it much more obviously. You have definitely multiple turning points, what we would expect if we, and some interesting fact here, what we would expect if we weren't just a single site. If you try to fit this to one single oxygen, it doesn't fit very well. It doesn't fit to a single quadrupolar coupling. Once again, this is fit to 4. But how do we know that it's definitely 4? Other than we did some neutron diffraction, and we looked at neutron diffraction in the literature, and they said, yeah, the crystal structure has 4 different water oxygens. That could be true. Maybe what we have is slightly different. Maybe it's not 4. Maybe it's 3. Maybe it's 2. Maybe it's 6. Maybe it's 8. It's really hard to tell. It's we don't have any way to do this. So what do? Well, we need isotropic peaks. It's no longer, before we only had 1, we're fine with MAS. We don't need isotropic peaks. We can look at the second order quadrupolar and pull it out. Well, we need isotropic peaks now. So we're going to move and we're going to do some MQMAS. We did MQMAS at 3 different fields. This one here at MIT. And these 2 spectra were done at the National High Magnetic Field Lab in Florida, one of them at 1500 megahertz and one of them at 800 megahertz. So you can see that at 900, we see 3 different peaks. So that's not what we expect in a 1:2:1 ratio. So that tells us that it looks like 2 of them are basically the same. So we thought, well, 2 of them are really close to the same. These 2 that are showing here are the fits of the isotropic projections of the MQMAS. When we go to 800 megahertz, we see 4 distinct lines, which if you fit this out has almost a 1:1:1 ratio because the 2 in the center are much narrower than the 2 on the outside. Why that is, I'm not entirely sure, but their environments must be much more homogeneous than the other 2. We were unable to fit this with a precision where we knew which water matched to which crystal site in the crystal. There just wasn't enough evidence in the crystal that could say which ones was which. The same thing is true here. These 2 center bands are narrower. The actual fits under the curves are close-ish, but this one here is not quite, at a 1:1:1. This one has a little bit less. Why? I'm not sure. Obviously, this experiment was taken, much quicker than the others because this magnet can only be at field for 8 hours at a time. So the experiment has to happen in an 8-hour time period. Somebody has to be there with the magnet because it runs powered, so they have to flip it on, they have to get it to field, they have to let it stabilize, they can take spectra, then they have to turn it off.
And you were talking about some vibrations yesterday also.
I don't believe, this one isn't that, this is the new series hybrid magnet. So
Oh, the
this
new one.
This is the new
Oh,
one,
right,
but you can
yeah,
only,
yeah,
you can only
yeah,
acquire
yeah.
spectra in like 8 hours. I think they can turn it on for a couple of days if you really need it, but you know,
It's not
this
their
was some of the first spectra that were taken on that magnet.
Those 800 spectra look so.
Yes, the 800 spectra also looks really good. What happens if we look at this
Just
a little bit closer?
I was just wondering though,
Yeah.
you know, you're interpreting the intensities and I was expecting you were gonna give some kind of caveat around that, or what's your feeling? On balance, it's probably as good as another NMR
So-
intensity, or?
No, so the reason why I'm interpreting the intensities, and this is a good question to ask, is because the quadrupolar couplings of these are all almost the same. So we expect the triple quantum excitation and conversion of them. They have very similar chemical shifts, so we're not expecting resonance effects of being off resonance. But no, in general, multiple quantum MAS experiments are not quantitative, they're qualitative. But in this instance, you can look at them and say they're probably going to be pretty similar, so they should have, you know, a triple quantum excitation and conversion that is similar in magnitude. So it's not necessarily that I wouldn't have fit these and said, oh, we definitely know it's 1 to 1 to 1. It was just more of this was 1 to 2 to 1, so we're saying, well, it's still 4 like we thought, but we're only seeing 3 peaks. So then just to look at this, you can pull out, so these are the slices out of these points. Yeah.
So what happened at 900? I mean, I know that the isotopic frequency is changed to magnetic field. Yes, but and those two peaks come too close to each other because
Yeah, so we'll get to that analysis. Part of it is that we're limited on our 900 and how much time that we can spend. They have far less limits at the National High Magnetic Field Lab because their 800 runs doing materials work most of the time on one of their 800s. And so this was run for a very long time, and you can see that the resolution in the indirect dimension, the isotropic dimension, is very high. We weren't quite that high here. I could get a week, so I could run the experiment for a week, but you know, that wasn't quite sufficient with our probe was also not the best probe for MQAS, so we're operating, you know, at I think half the field strengths that they can run on their HX probe at 800. So though that's some of the differences. They also did a different type of MQMAS that was just better. I would do what they did if I did it again, but you know, this was probably taken in 2014, and this was taken in 2017. So we worked out the data a long time before we ended up with the other data. So right here we have the slices out of each isotropic, the center of each isotropic peak. And, for 35 Tesla and for 18, and then these are fit with, this is not just an MAS kind of spectrum, it's a triple quantum filtered frequency, so the shapes are slightly different. They don't look like just the CQ that you have from the central transition, because you're getting, the triple quantum characteristic from the other transitions that you have, which have different interactions going on. So you see, these were fit in a program called DM fit. That does this in the frequency domain, so it just fits in the frequency domain. So you can see that the spectra look fairly good, particularly here at 18 Tesla. And I've put up here the fits of the EFG and CSA tensors based on all of these different results. So this is all the data goes into how we got these fits. Every spectrum we've seen were the fits that were shown were from this set of data. So afterwards, I had, lots and lots of bits of the 4 sites just on the data we had, but, everything else went into this. So you can see that you have, while you have different isotropic frequencies, you have isotropic chemical shift frequency that's fit out because we have multiple fields now, of about 8 ppm difference. So they're about 2 or 3 ppm difference in each one. So it turns out, as you can remember, and here in this one I showed, not resolved, there's only one peak at 12.6 ppm in the 900 data. So why is that? Well, it actually turns out that 900 is about the crossing point for these two pieces. There's an equation you can do to calculate the isotropic shift or the triple quantum shift that you see. You have to do some calculations using the quadrupolar, the EFG tensor, to basically get rid of the second order quadrupolar isotropic frequencies. And as you can see, you can follow sort of each of these peaks as they move through the space experimentally. And then here's just the calculations that I did, which show pretty much the same thing. So I'll get rid of those. See what I have on there. But you can see that, it just was hard luck on us that our first data point was right there. And it turned out that while we had access to an 800, the only probe that we could do experiments on was a 1.3 millimeter probe, and we just couldn't get efficiencies good enough on the MQMAS with the small amount of sample that we had to do an MQMAS experiment on that sample in that probe. So
Eric, did you say why you picked 3 quantum?
yeah, so I didn't. So obviously you can do, it's a spin 5 half nuclei, so you can do 5 quantum. 5 quantum would get you narrower, but significantly reduce your sensitivity due to the much lower conversion rate of the 5 quantum conversion, excitation and conversion pulses. We were operating on a level of about, on the 900, about 4% efficiency. So it just was prohibitive. Even at 3Q, we were having trouble with enough sensitivity.
So did you know, based on, you thought the quadrupole coupling was that would be likely to be the sweet spot, like just looking at literature, or did you just try that first?
Yeah,
Because
it's generally the first place to go. I mean, you won't see very much, other than 3Q MAS. The triple quantum MQMAS is almost everything that's out there, even if you're working with something that's 5 halves.
Okay.
Mostly just because you lose pretty much at least another order of magnitude in efficiency. And most of these are operating on the order of a few percent efficiency. So partial percentages it's really hard. I also tried satellite transition MAS, but our probe was not good. It couldn't hold magic angle well enough. I couldn't get it accurate enough. It was because this was on the 900, it was a standard bore probe with a flip angle stator. So the difficulty in getting an accurate enough magic angle, I couldn't get the experiment to give me better spectra than the MQMAS. They're far broader isotropic shifts. So.
And did you say something about the different environment? Oh, you said that you weren't sure which was which?
Yeah, I don't know which was which what. So I don't know which of these corresponds with which of these. So I don't know, if this one is the one that's at, -5 ppm isotropic, or, this one, is the one at 0, and this one's the one at 2 or whatever, and this one's the one at -3. I don't know that that's true.
No, you did not turn to DFT and opportunity.
It is not gonna get the chemical shifts that accurate. So that's the problem. We have DFT, it didn't point us in any direction. I spent years, trying to figure out if I could identify one with a precision that I would feel comfortable putting it in a published paper.
Now, this is lanthanum itself, not a generic lanthanide.
Yeah.
So it's diamagnetic, the whole thing is diamagnetic, yeah. Yeah, sometimes people see LA and they're thinking, oh, aren't those all paramagnetic or something? Yeah.
Yeah.
And do these materials show up in any kind of like application? Are they?
Not
Nothing
that
that-
I know of. I don't remember why we chose this particular one. I don't know what
Well, it's an
the,
interesting system, but
I mean, part of the motivation was that it is easily doped. So we actually did do some DNP on it. We gadolinium doped it and looked at DNP on the different nuclei.
interesting.
So that was, so this was a sample that was floating around before I started. Vlad, Michaelis, and Bjorn Berzelius were working on it for various reasons. And Bjorn was always interested in doing something with a metal center for DNP, so.
Yes, right.
So that was part of the reason. So it was around, we knew how to, deal with it. Vlad had already labeled it with oxygen, so. It was a good test case. So the big thing is that the idea, the motivation, I guess I could have put a slide to kind of put that out there. The motivation for this is that in multiple samples in my graduate lab, there was this idea of water pockets or intercalated water in structures of things like GN and QQ&Y and TTR fibrils. And so the motivation for trying to study these bound waters was to try to actually look at the waters in those samples. So in the case of GN and QQ&Y, I think it's 7 waters that they have put like in the structure that's in the pocket is what they think. There are 7 bound waters there. So the idea was, one, is there even a chemical shift distribution? Can we, even if we had multiple ones, can we resolve them from a chemical shift standpoint? We showed that they're bound to different amino acids. Probably there's a chemical shift dispersion there. It's not 0. They don't all just show up where ice shows up. Then we looked at some of the difficulties with the barium chlorate. That was kind of a test sample, but then because of the NQR data, we decided to go low to see if that was what was causing the EFGs to be bad. And then this was, if we do have multiple of them, we have a crystal in here that's saying there's multiple, can we do any sort of resolution?
And this is again at room temperature, what you just showed.
Yes, everything is at room temperature, except for the barium chlorate
Yeah.
experiments. Everything's at room temperature.
So you tried dynamics also on this?
What do you mean by dynamics? On this one?
Yeah.
No. These are just oxygen 17 experiments. There's no dynamics experiments. But there's no reason to think that, based on what we have here, those CQs and ETAs are right around the other ones. There's no reason to think that they're not undergoing the same dynamics as any other bound water molecule. I mean, in fact, I do know that I have deuterium spectra at room temperature and at low temperature, it hops. So I could show you them.
I like deuterium
But,
spectrum. Why would you hide your
I have-
deuterium spectrum from us?
I'll have deuterium DNP spectra of the element, the gadolinium doped element. In case you were wondering, Okay, so then what's the next step? So now we've shown, that we can do isotropic spectra of this. Check. We can, resolve chemical shifts. you know, so what's the next step? What do we want to do next?
Protein model.
You want to do protein water, you're jumping straight into protein water correlations. What do you need to be able to do protein water correlations?
Anything?
Yeah, so maybe we should see, can we correlate this? Can we do correlations at all? Before we jump to the protein experiment, I mean, it's always great to jump straight to the thing that's really, really interesting.
No, just
but-
KCSA.
So correlation spectroscopy.
Oh,
All kinds of literature out there with correlation spectroscopy. You'll find that, you know, it's a veritable alphabet soup of things. So I've just listed a few. You can do cross correlation. You can do het core. That's just, you know, a fancy way to say cross polarization in the other direction. You're not enhancing, but we're directly detecting on just the regular heteronuclear correlation experiment. So if we want to do a proton oxygen dimension, we, you know, detect on the, you know, the proton or the, you know, either one, but we can just do that. You can do REDOR, you can do TDOR, you can do REAPDOR, you can do TRAPDOR, you can do RESTDOR. There's all of these. They're just, you know, acronyms. REAPDOR is just an adiabatic passage REDOR. TRAPDOR is similar. It's a little bit different. It uses a, you know, hard long pulse instead of an echo train, but they do very similar things. You can do dipolar-based HMQCs and HSQCs, you can do dipolar-based inept experiments. I took this out of a review by Jean-Paul Amaro, where he just looked at where things had been done and where things hadn't been done. It's from quite a while ago, it's from 2009, so that there's more of this that's been filled up, and I just thought it was a nice diagram, where if we look at, you know, our spin being, you know, homonuclear spin I. If you're spin 1, there's nothing out there at the time that correlated, you know, deuterons to deuterons in a homonuclear experiment. But, you know, there's development on spin half to spin half, where it's not, where one of them is not 1/2, but is in half. Obviously they're homonuclear, so they have to both be in half, one's in half. Spin, you know, 1/2 to in half, heteronuclear, there's lots of stuff out there to do that. In half to in half, that's harder. So two different quadrupolar nuclei interacting with each other, that's a harder problem. There's a lot more interactions that are going on.
this diagram hurts my head.
So you see, these are all just, you know, spin 1 to spin 1/2. It's out there, you can do it. There's experiments for it. You know, in half to 1/2 or in half to in half and heteronuclear. IS spin is a little different. So, you know, these are J-based experiments. These are dipole experiments, you know, kind of splitting here. So, you know, dipole J. But it turns out that there's a lot of this space that is empty. And part of that is just, you have to be motivated and you have to have the right nuclear combination in your sample to need that experiment. You know, unlike our general thinking, labeling is not big outside of biomolecular NMR. So most people don't label their samples. They try to find a nuclei that has a good enough natural abundance that they can just take the spectra on it. Can be fairly expensive or just prohibitively difficult to try to label.
It's also worth mentioning that for applications in materials or in pharmaceuticals in tablet form, I think from the point of view of kind of view from 20,000 feet within the company, they don't want a different batch that was made by a different way,
Right.
that has different impurities and different this and that. They want the stuff that they're actually selling.
Yep.
So even if you could C13 label your pharmaceutical tablet, they don't want that spectrum. Or they don't want to
Exactly.
pay for it.
Exactly.
Mhm.
So then, can we do it? Well, we can. So this is N15 carbon REAPDOR experiment that I did at 750. So this experiment is on N-acetyl-VL. That was labeled 70% with oxygen and uniformly labeled in carbon and nitrogen. So this experiment is just like a, regular reader experiment. The curve just looks like a regular reader experiment. Instead of just a pi pulse, you have a hard, it's actually not that hard, but, you have a, 1/3 rotor period length pulse on the oxygen in place of that, to better refocus that quadrupolar nucleus. That's the only thing that's happening on the quadrupolar nucleus. Everything is just regular nitrogen detected. And then we can detect these buildups and we can fit them to distances just like we would anything else. Here, each curve here, it has to be simulated using 2 distances. Kind of hard to see, they put it up at the top, but the blue curve is these 2, and I'll change colors. And the red curve is that one to those, these nitrogens here and here, should have done them in colors. Go back and do that actually. If we, the red nitrogen here and the blue nitrogen or the blue curve there. So there's 2 different nitrogens, the valine and the leucine nitrogens, and they each have 2 oxygens that are close enough to interact, one of which is happening between 2 NaDl blocks. So not just,
The close hydrogen bond.
yeah, so that's the closest hydrogen bond. Yeah, and it's about 3.2 angstroms between
What's,
the nitrogen and the oxygen.
what is the isotopic composition of this NA?
It's uniform 13C, 15N, and 70% 17.
And the proton's normal.
Yeah, and propane. So
So it being 70%, hey, I'm a nitrogen and I'm looking out at my oxygen, so sometimes I have that one. Oh, sometimes I have that one, and sometimes I have both, and is that all baked into these simulations?
yeah, you have to put a scaling factor based on the percentage of labeling.
It's cool, that it's
Delta S
possible.
over.
Super cool.
So that's why they don't go all the way,
Mhm.
because these are pretty strong. So then, can we do anything else? Well, we can also do just, TDOR, oxygen to carbon TDOR. So that's what I'm showing here. This is just a simple TDOR experiment where instead of pulsing on nitrogens, we're pulsing on oxygens during the readout periods. And you can see that we can do not just, 1Ds, we can do 2Ds, and we can see the different oxygen carbon interactions here, where this is just an MAS dimension. But as you can see, this is pretty broad. You're not seeing much here. The signal noise is low because of how broad the peaks are. It's not really that low of a signal noise, but when you take and look at your spectrum over the course of 50 ppm, your peak doesn't show up well in a contour diagram. You don't have a lot of contours up there because the integrated intensity is what you're looking at. So the next step is, well, shouldn't we be doing isotropics? And the problem is that, this is not super high efficiency. TDOR isn't, that great. And then you have MQMAS on the top of it. So what does this look like if we just look at the curve? So you can see the efficiencies of these TDORs are very low. This is some of these, like this one right here. This is a single, OH bond, 1.2 angstroms. Our efficiency is about 1.6%. Is as much of the carbon as we're seeing in comparison to a CP experiment. These simulations were from, nothing to do with them. Spin evolution. So different program, does pretty much the same thing. It just turns out that the TDOR experiment worked in that simulation. I couldn't get Simpson's TDOR to work.
Now, some of the carbons have 2 oxygens.
Yeah, well, because this one is the you know, carboxylate group. So so this leucine one has to have two,
Mhm.
because it's just a dipeptide, so you have
Terminus.
the terminus there. So then what about the other ones? Thought I didn't show them, but I have the two other, carbons, the C alpha carbons as well, and you can fit them to their distances as well. So then what's the next thing? Well, let's do something even different. Let's do proton detection. So we'll proton detect DR inept experiment. So using rotary resonance pulses in the inept, we're going to do dipolar inept. And then we're going to look at the proton spectrum here in correlation with the oxygen spectrum. And you can see that we can get three different correlations here. This one is fairly weak. That's the same hydrogen bond. Across here, you have a hydrogen bond across this way as well that exists. This is a hydrogen bond that we can't detect with the nitrogen one because it's not between an NO here, it's in the other direction. So, you know, the N is way over here. It's not next to the oxygen, and it's not the NH proton. So you don't see that in the Reef door experiment. It's a little too far to have a strong effect on the Reef door. But in the OH, we see this, and we see obviously the very short, you know, just OH correlation.
Is this a deuterated cell?
No,
So,
this is protonated. This is at 750 spinning just at 20 kilohertz. So you can see how broad this is. It's a small sample, and we're filtering out everything that's not attached to oxygen. So the line width of the proton is not that much of a worry because mostly we're seeing amide and OH protons, and there's only a few of those.
so are the green and the blue peaks, cross peaks, showing up at that same acid proton? Is that what?
I mean, it's hard to tell. It's too broad to tell if those are actually the same. They shouldn't be. Actually, yes, they should be.
Should be,
So-
and they do,
and
and
they
it
look
looks
pretty
like it
close.
is,
But
although
the
there's
problem
something
is
funny
that,
in the
you know,
line shape.
Well, that's because of the broad quadrupolar line shape and issues with that. It's part of why the line shape.
And
is
then you
kind
have
of
the
funky.
one amide proton.
Yeah,
So
and
as
there's
far
the
as
one amide proton.
protons, it's mainly these two protons, right?
Yes.
That's cool. And how
Oh.
was the efficiency when you went to proton instead of carbon?
It's still very poor. So that's the problem. I mean, you can see that this is, you know, very low signal noise, see lots of noise in that. This is, if you plot it out and you can't see this one, it looks a little bit better because we don't have quite as much noise on all the spectrum, but we're really, you know, into the noise here with that amide peak. Okay, so, well, we have correlation, but we want resolution, but we also want sensitivity. So we can add a high resolution isotropic technique like MQMS on the front of this DRNF experiment, but now our efficiency is going to be far worse and the sensitive issues abound. So we have to be a little bit more clever about it. One thing I want to talk about is the way I labeled this sample. I should have put this at the beginning, but one, we need to label it as best we can. I talked about acid catalyzed exchange. This was a reaction that I should have put the citation for here. I apologize for that. That I found that was used to do O18 labeling for vibrational spectroscopy, where it's using protected amino acids. It's just a multiple turnover reaction. It's a, you know, single pot stir kind of reaction. You just put everything together, you let it stir, you add, you know, activating agent a couple of times during the experiment, and then, you know, you do an extraction and get out your amino acid, and you recrystallize, you know, your mock protected amino acid at the end. has a carbonamide activating agent. It does multiple of these turnovers over and over and over again. You have an excess of water, you have an excess of, this EDCl that you add more EDCl, every 18 hours in the experiment as it's written. You can actually shorten that down to every few hours and still get really good efficiencies. The efficiency is, approximately better than 90% of the labeling, which is pretty good. Acid catalyzed exchange usually tops out at about 65 or 70%. And it's under mild conditions. So what else can we do? Well, we can try to do some sensitivity enhancements. Well, we can try to use the satellite transitions. This is an idea that goes really far back, as you can see in the slide, I got from Bill Graniti, first described by Pound in 1950 to, use satellite transitions to enhance your central transition. You can do it in two different ways. You can saturate them. I'm just showing that here. So you can saturate your satellite transitions and you get an effective enhancement of I plus a half on your spectrum by saturating your satellite transitions. You can also invert them and then you get a 2I enhancement, but that's a lot harder when you're not looking at single crystals. Your satellite transitions are broad, as you can see here. So what's one way we can do this? We can do this, what's called RAPT, rotor-assisted population transfer experiment, where we put low-power Gaussian pulses at frequency offsets from your central transition, one at plus and one at minus, with X and minus X phases when we're spinning at the magic angle. And we can do a little bit of saturation on the satellites and get a better experiment. There's other ways to do this. You can then do this multiple times and do multi-wrapped. You can apply differential frequency switch pulses across these offsets to try to invert them. You can do hyperbolic secant pulses. They actually work really well. So you can apply a hyperbolic secant pulse offset. And these offsets are hundreds of kilohertz from the center of your spectrum, usually on the order of 600, 300 in that range, kilohertz offsets, and powers on the order of tens of kilohertz.
So no matter what the rotor does, you're never going to be hitting your central transition, but your satellite transitions are going to pass through these conditions.
Sorry.
And like in a timeshare way, you're going to eventually zap them. And what about their T1? Don't they just come right back, or what do they do?
Yeah, so I mean, the tau here is pretty short, so you're going to then immediately hit the central transition with the pulse and acquire. But yeah, they will come back, obviously, but the idea is that you're doing this right before you're acquiring.
It's just a cute idea.
Microseconds before. Or you can apply worst pulses on them as well to try to invert the satellite transition. So basically any kind of pulse that you use for selective inversion or selective saturation, you can just apply offset and try to enhance your signals. Typical enhancements aren't anywhere near, I plus a half or 2I, on the order of 3 or 2.5 signal enhancements, but it's essentially for free because all you have to do is apply a few pulses beforehand. They're low power. They're milliseconds long, but they're low power, so there's no high risk to the probe. Okay, so what if we do some of these other fancy things added onto it? So, this stuff come out, recently. This is the same NAV sample, that's been down at the Magnet Lab since 2017, that they just keep doing more experiments on. Just fun. I get, every once in a while I get a report of, hey, we did these things, and we write a paper. So this top spectrum is just proton to C13CP. So we're just activating the C13s here. We just did proton to C13CP. That's kind of the standard. We just do regular CP like you would. Nothing fancy about that. Now we do oxygen to carbon CP. So that's essentially the same experiment, except for right here. You can't really read it, but at the beginning, before we hit it with a pulse. There's a 450 positive 450 kilohertz offset worst sweep 90 kilohertz sweep pulse that is for a millisecond. It's a 12.4 kilohertz pulse, and that's just to enhance the oxygen 17 satellite transitions to the central transition before we knock down and then spin lock on the central transition and try to simultaneous spin flips to the carbons. You can see here that you get a spectrum that looks pretty similar. It's got a little bit less signal to noise, but it's acquired in half the time. And then we do something like O17 to carbon, DRNet. That's just the experiment down at the bottom. Just a simple experiment that is exactly like what I was showing on the other one, except for we're going from oxygen to carbon, not proton to oxygen. So we're detecting on the carbon. So now what we're doing is we're gonna do the same thing we did with sort of Breitdor and T-Dor. We're gonna indirectly detect the oxygens, like we've been looking at, because the oxygens have broad spectra and low sensitivity. So let's try a higher sensitivity nucleus. Why don't we try protons instead? Instead of carbons, let's do protons. So let's spin fast. Let's spin at 60 kilohertz. Let's put it in 1.3 and spin at 60 kilohertz and detect the protons instead of anything else. And let's start with the oxygen and then detect the protons instead of starting with the protons. So that's what we're showing here is, this OCH experiment. That's this trace here. This is the HOC experiment, or this one here, and then this one here. And so you can see that you can do either. You can start on the protons, CP down to oxygen, then CP from oxygen to carbon, and then back to proton. That's sort of figure 5A on the bottom. Your signal to noise per scan is higher than if you start with the oxygen and you just go directly to the proton. So even with the unfavorable, second or two cycle delay of the proton in this instance versus the millisecond for cycle delay, you're still favorable starting with the high polarization of the proton and doing a CP of the oxygen before you do it. So, and it's a little bit off, but I mean, you're still good both directions. So you do either of this. So now what can we do? We have now we have really fancy experiments. Now we're, they're starting to look like solution pulse sequence diagrams now, with all of these different shape pulses, on the carbon channel here. This is getting a little ridiculous, all kinds of pulses everywhere, selective, unselective. So what can we do? Well, now we can do 2Ds and 3Ds and really look at what we're doing here. And we can add MQ to the front of it and get narrow lines. So now what we have is we have these multiple 2Ds that are being shown here. We have, two different alpha protons, the leucine and the valine up at the top. We travel down this, looking at the correlations of the C alpha to those two protons, and look at the COs in this OCO-CAH experiment. We're not detecting the C alphas here. We're only detecting the COs, and then the protons up here, we're only detecting the CAs and not the COs. We're not getting both planes at once. It's not a 4D experiment. It's just a 3D. The experiments that have the overbar shown, those are isotropic oxygen dimensions. So they have an MQMAS at the front. That's, the green piece here. A little bit different shape looking MQMAS than I showed before. It's just a different style. It uses long, low pulses to get better efficiencies because of the fast spinning. So then if we look down at the two oxygen dimensions that are shown, in the two experiments with and without, you can see this delta in the center of gravity shift to the isotropic frequency, and you can see the breadth of this yellow-orange spectrum versus the narrowness of the isotropic shift in that, in this case, in the valine oxygen. So the valine just has the single CO, when we look at the leucine plane, where we're only looking at the leucine CO carbon, we have two different peaks, one for the COH and one for the C double bond O.
And
sort of
again,
characteristic.
that green is if you have multiple quantum,
Yes,
detection
the
and,
green spectrum is
yellow is just like what you get at that
yes.
spinning frequency as
Yeah,
a,
yellow is just your MAS, you're just doing MAS at the beginning.
very nicely, it's very satisfying and nicely laid out, so you can understand the story.
So you can keep on keeping on at this, and let's say we want to look at them in the other way. So now we have, this O COCA experiment. We're going from this O to the carbonyl to the C alpha to the H alpha, and you get the blue spectra here. And then what if we then do DREAM on that experiment? So we're gonna not digitize the CO dimension, but we're gonna digitize the CA dimension after we do DREAM, and we do O to the CO, to both C alphas, to both H alphas, and then we get the red spectra, where we can see the valine and leucine C alphas in their respective oxygen peaks.
How do you do the CO to CA transfer of the experiment?
In the top experiment, the CO to CA transfer, it's complicated. So I think this one might show it a little. I don't know if I have one that actually explains it, and I'm not. It's using basically shaped pulses to resonate on the two.
Oh, okay.
So it's,
Some sort of frequency selective.
yeah, it's frequency selective homonuclear pulses. That's happening. I don't remember exactly what the name of what they used was, but yeah, I mean, it's shown here, as I said, it's, we're in the regime of where things are looking like solution. I don't even know, I can't recall if what Ivan did was even dipolar based, or whether they used a J-based experiment, because they're spinning at 60 kilohertz, so you can do the J-based experiment, so it might even just be a solution.
Now, can you say again what's going on with tie down to that oxygen experiment, the
Right.
1D below?
So
What's
this
happening?
plane here
Uh-huh.
is looking just at the valine.
So you get a
CO.
correlation in another dimension.
Yes.
Just to that one peak. It's
Just to
clean.
this peak. And in this one, you get the correlation to these two peaks.
I see.
Because it's,
And
the other.
that's the terminus
CO,
with two
yeah.
oxygens.
Yeah, the terminus has two oxygens, one of which is H bound, and one that doesn't have the H. If you have the instance where you're Zwitter ionic, you don't get two peaks, you get a single peak of the two. So if you have sort of, instead of being COOH, you're actually C like that.
You had a case or a bunch of cases that were like that.
You can look them up in literature. When you have ones like that, a lot of times this happens with. So the reason why the NSCLVL, because you have the bonding network, you get the proton there. But if you take the protecting group off this, a lot of times you'll form, in some of the amino acids, you'll form the Zwitter ion. And then you just get.
Or is it just a salt? Is it like, who's the
Yeah.
counter counting? So
Yeah, usually it's a salt. You end up getting a salt crystal out instead of, the pure crystal.
thinking about the carbon database, which is different in terms of like the point of view of the measurement, but
Right.
there, you could really distinguish different kinds of anions for different kinds of protonated states. But for the anion here, do you think there may be oxygen exchange? So even if in principle there were a different environment, you're not going to see it? Because normally the environments are pretty different according to
Yeah.
point of view of the carbon, but that
Yeah, I don't know, I'm not 100% sure, so. I
It would
mean,
be interesting to know if the oxygen is exchanging in those anions. If they really are equivalent, and it smells like it is,
Yeah.
but then you'd have to do the whole temperature dependence to be.
yeah, I don't know, usually it's just hard because you don't really get, you usually get, some amorphous. It doesn't really like to crystallize, when they end up like that, in my experience.
You'd have to pick one that's nice and crystalline. There
Yeah.
are some, but you have to pick it carefully.
Yeah, you'd have to get a good system.
And then you have to be able to label that system.
I just know this because there's another saponification reaction that we tried, and it actually turns out that one of the reactants will cleave some of the protecting groups, but not like super efficiently, just kind of a little bit. And so when I would try to recrystallize them, I'd get like 50%, crystals and then 50% of this giant broad peak in the middle.
Mhm. It makes
Because I was
sense.
getting this sort of zwitterionic,
Yeah,
amorphous junk in when I would try to crystallize out because they weren't protected anymore. So I forget which amino acid that we were working with at that time, but it wasn't, I don't think it was either valine or leucine. I think it was a different one. Okay, so you can do this, and we can keep going, and we can now add nitrogens into the mix if you have a nitrogen oxygen probe. In this case, now we don't have any carbon dimension, we just have H and O. They have people at the National High Field Magnet Lab that are really good at building probes, so that's why they're able to get a probe that does this. This is just the experiment up at the top here. That's being shown here. It's the O, H, and H experiment. So we're starting with our worst pulse on oxygen. Then we're digitizing the oxygen dimension, doing a CP, up the proton, and then straight back down to nitrogen, digitizing the nitrogen dimension, water suppression, CP back, detect. And we get the spectrum that's here. It's the spectrum not in, no, it is a spectrum in pink here. In a 1D, the spin echo just looks like this. This is not spinning particularly fast. We're spinning at sort of 16 kilohertz or so, I believe. Well, maybe not. No, it looks like it's spinning at 60. This is 60 kilohertz. Sorry. It just looked very broad, but it is because it's an amino acid that has pretty strong coupling. So then in sort of a 2D NH, HNH or a 2D OH, you get these blue and green spectra. Those are just sort of the symbols, proton CP, proton to nitrogen, nitrogen CP back to proton detect. You get, the two peaks shown here for the nitrogen at the leucine and the valine. When we do the oxygen version of the experiment, we only see the peak on the valine. We don't see the peak that's the leucine peak. If we do the 2D OH, we see all three of these with the protons that we expect. Two on the acid and one that's on the amide. Then if we do the same experiment down at the bottom, except for we add MQMAS to what we are doing here, we see that we have very narrow peaks now. The blue spectra and pink spectra are now narrow peaks that line up exactly where we would expect. And then we can do this experiment where we do rest door, another type of technique to correlate, spin 1/2 to spin 3/2, and we can measure this sort of coupling here between the two. But what we're doing in the spectroscopy is we're not going through directly from oxygen to nitrogen, we're going through the proton, and that increases our sensitivity. And allows us to do the experiment where when I was attempting, these sort of 2Ds between O and N, the sensitivity just wasn't enough for me to acquire it. But adding the proton allows it, we spin at 60 kilohertz and we can do it. Imagine spinning faster, we can still do it, but We're still, once again, just to remind it, we're at 70% oxygen labeling, so we're very well labeled with oxygen, so it's still an ideal case scenario, small molecule, lots of spins. Okay, so that's what I've done with it. So now I was just gonna go over a couple of things for a few minutes if we have time. I don't know if we do.
I have to do something at 3, but like
Okay.
a couple of minutes is perfect.
Okay, so there are also experiments to correlate spin 1 to spin 1/2. This is an experiment called respiration CP to do CP from deuterons to spin 1/2. It's developed out of the Niels-Nielsen group. It uses these trains of pulses on both the proton and the carbon instead of just standard. You start with a preparation, doing respiration on just the deuteron before you do the respiration CP to help enhance the deuteron signal. You can do this in actual samples. This is out of the Mahon group. Marty Blinter did this with just bacterial cellulose labeled, where he took and ran, 2D spectra, deuteron, carbon experiments and fit them out to look at the different deuterium sites in that, and to look at water dynamics in the cellulose. Other studies you can do. This is a study recently, in 2020, out of the National High Field Magnet Lab and Tim Cross, where they looked at oxygen-17 interactions with water in grammacidin A in the pore, in the transmembrane pore. They labeled the bilayer, the grammacidin, selectively with O17's amino acid specific, and then they took oxygen-17 spectra of each amino acid specific site and looked at multiple different chemical shifts that were happening in this. This is calculation versus experimental differences in chemical shift between the free and the bound sort of water instances. So that's what you see with the asterisk is those differences. Here's another look at it where they looked at its dependence on the amount of potassium ions and looked at where their potassium ions were strongly or weakly bound. Strong binding, weak binding potassium, and you can see near L14 prime, L14 on, you have the sort of weak binding, and it's L10. It's strong, so you see the strong shift of that. So, and there's many other studies. Here's a study looking at deuterium and O17, looking at waters, and their interactions in a mineral phase. And then, just some more studies on doing similar things with, so it's in yeast ubiquitin from the lab of Gong Wu. More studies from our friends at the National Field Lab, Ivan Hung and Seon God, along with Gong Wu. So, and then I just put this on here, our capabilities. We have this Phoenix probe. It can tune between phosphorus and carbon on the X channel and sodium and N15 on the Y channel. We have a 1.6 and a 1.2 millimeter rotor for that. And we also have a 2.5 millimeter black box. It can tune very selectively to a few quadrupole nuclei. Most interestingly, it has an HCD tuning mode, which means it also has an HC lithium-6 tuning mode if you're interested in doing lithium-6 NMR. And the HPC mode can tune to aluminum and sodium. I presume that the carbon on the HCN may also be able to tune to those, but it doesn't explicitly say it, which means it probably doesn't. The 600 DNP probe has the same tuning range as the other Phoenix probes. It's tunable all the way. That's an HFXY probe. Has fluorine capabilities as well. It's not a quadrupole nucleus, but is another nucleus that people might be interested in. And that is all I have.
That's fantastic. I mean, what a great overview of things people are doing and things we could be doing, and it's fantastic. Thank you.
Of course.
Really appreciate.